Good afternoon, everyone. I'd like to thank you all for joining us today for our weekly webinar series. Today our featured topic is fiber characterization. My name is Jessica Petrohoy, and I'm the marketing coordinator at fiberoptic.com. Fiberoptic.com is a leading provider of fiber optic products, training, and rental equipment. We're pleased to present this topic to you today. With us today to talk about fiber characterization is Terry Power. Terry is one of our senior instructors and a field technician with over 25 years in managing and testing networks. When Terry is finished, we'll take questions from the GoToWebinar question box at the bottom of the screen for a question and answer session. Remember that our webinar series are recorded and available to you online at fiberoptic.com/webinar. So thank you again for joining us today, and at this time I turn the presentation over to Terry.
And good afternoon, everybody. Again, my name is Terry Power. I am a senior instructor and manager of training here at fiberoptic.com. A little bit about myself before we begin. Started doing cable television work in 1987. And over the years, fiber pushed deeper and deeper into the cable plant. I started working more and more on the fiber. And worked on hurricane recovery in 2004 all over Florida, and ultimately in the Cayman Islands working on Hurricane Ivan recovery. From there ended up in Barbados and was made outside plant coordinator for Tele Barbados in 2006. 2007 they sent me to the fiber school to get a certification so that they had a little record of everything that was already on my resume. And I met the president of the company here. 2009 I moved back to North America. The company here put me on salary, and I've been with fiberoptic.com since. I have run crews in the field all over Connecticut, New Jersey, New York. Have done testing jobs all over the world and training all over the world. And today we're going to talk about fiber characterization. Now this is some of the testing jobs that I talked about, that I just mentioned, were characterization jobs done in the field, working with clients in, I don't know, Panama, Guatemala, all over the U.S. So anyway, so we're going to talk a little bit today about characterization. Now this is going to be kind of a high-level overview. We're going to talk about some of the tests. We're going to talk about what is characterization. We're going to talk about why it's important, probably the most impactful and significant part of this presentation. We're going to talk about the tests that are needed when you do full characterization. Now, according to the ITU, the ITU-T standard G.650.3 defines fiber characterization as a comprehensive suite of measurements that are carried out on an optical fiber cable link to determine the key performance attributes of that link, which may affect current or future application that operate over that link. I know that's a whole lot of words to say. Basically, what we're going to do is some tests that will tell us what our capabilities are. We're always going to be limited by certain performance attributes, as is worded in the definition, that are going to create limits on distance and bandwidth. And we want to test for those and learn what we can do to mitigate those so that we can go further and faster. Anyone that's listened to any of my webinars in the past, you will know that I'm always talking about fiber development is always about going further and faster, further and faster. And characterization helps us to look at the performance attributes of the fiber itself and determine how far and how fast we can go with the current fiber that's in the field. Now, why? You know, we're always going further and faster. Well, here's a a slide that demonstrates the growth in the need for bandwidth. And we're looking at, 20 gigabits or gigabytes per month. This constant growth, and you see that curve is not a nice straight line. That's a nice sweeping curve, and it gets more and more every year. And it's all about the peer-to-peer, that's that darker yellow at the bottom, and about video, which is the blue section. And video is really driving the growth. You see the curve, or the line is pretty straight. The growth line is pretty straight on data and on the peer-to-peer, but the blue section is exploding. And more and more, as people move away from pay TV and go to on-demand type of programming, we're going to see an increasing demand for bandwidth. Video is driving this whole process, and we've got to make sure that we're keeping up. So fiber characterization allows us to see what bandwidth we can push across existing fibers. Excuse me. We're going to be able to document the fiber plant. We're going to qualify the integrity and the workmanship of the installation. We're going to, and that's of course with a new installation, we're going to look at, can it support the transmission equipment we're trying to use? And we're going to look at all of the limiting factors. Now here's the testing that we're going to be looking at. We're going to look at span loss. We're going to look at our individual losses, whether it's splices or connectors. We're going to look at optical return loss. We're going to talk about each of these in turn. Polarization mode dispersion and chromatic dispersion. Those last two are really our big roadblocks. So once upon a time, the first fiber networks, this was pretty easy. We were working on a single wavelength. We were at 1310. We were going about 50 kilometers, and we were throwing in a regeneration site where we would receive the signal, convert it back to electrical. We would check all of the clocking pulses. We'd reclock it, retime it, and we would send it to a transmitter, and we would transmit a brand new signal. So the existing signal had to hold together for 50 kilometers. No big deal. The second generation came with the realization that 1550's got the least loss of any wavelength. We then could stretch out to 85 kilometers before we needed a regeneration site. Again, the regen site's going to have that optical to electrical to optical. It's expensive, and it's a limitation. Then we found amplifiers. With erbium-doped amplifiers, we can amplify the signal and send it on. Now, of course, if there's any dispersion or spreading out of the pulse, it doesn't get reclocked and refixed and timed and everything. It just gets sent on down the line to get more dispersion. We'll talk about that in greater detail. But then we came out with dense wavelength division multiplexing. And this is allowing us to combine multiple wavelengths onto a single fiber, take them apart on the other end, with erbium-doped fiber amplifiers to allow us to push it further. We are now allowed to cram a whole lot more information onto that single piece of glass. But the signals are getting very close together. And therein lies one of our issues. So we have to look at our increased bandwidth. We, of course, want to reduce costs. We want to create revenue. I mean, if it's not generating revenue, why are we doing it? And we want to provide competitive service so that we stay out in front of the competition and all the other guys. So the tests that are required. First thing we're going to do is visually inspect all of the connectors. We want to make sure that everything's clean, no scratches or cracks or chips in the fiber. And we want to make sure that we're starting with a good, clean connection. I will tell you that cleanliness is probably the most important aspect of any fiber plant. As I said, I've traveled the world and I have been to parts of the world to troubleshoot problems that were solved with a cartridge cleaner and a quick click connector cleaner, a bulkhead connector cleaner. It's amazing how a little bit of contamination on a connector end will kill your entire link. So I cannot stress strongly enough the importance of cleaning and making sure that you do a visual inspection and verify the quality of your connector ends. Then we're going to do a bi-directional, well, these are not in order. Okay. The tests are also going to include bi-directional OTDR testing at the wavelengths that are used, and usually one higher, which will allow us to identify any macro bends. We're going to do bi-directional loss testing with a power meter and light source, because however good an OTDR is, the power meter and light source is still the most accurate means of determining loss, because ultimately the OTDR, or the power meter and light source, is a direct power reading, and that's always going to be more accurate than a return reading that you get from an OTDR. So that tier 1 power meter and light source is still valuable beyond measure to the testing process. We're also going to look at optical return loss, both A to B and B to A, and we're going to look at this typically at 1550 because that's in the C band where we're operating most of our dense wavelength division multiplexing, or DWDM. That's also going to be indicative. The results of that ORL testing will be indicative of how clean our connectors are. So cleanliness is going to go to ORLs. And then our polarization mode dispersion and CD dispersion, or chromatic dispersion measurements, are going to be the other tests that we run. So some typical issues when a fiber characterization tech arrives in the field. Some of the things we see. Wrong fiber assignments. I can't tell you the number of times I've been sent out to test 2 fibers and find out those weren't even the fibers I was supposed to be looking at. Or something is connected to them and I can't unplug them. Any number of ways that incorrect data keeping has led to some tech being sent out to the wrong fibers. Sometimes we'll find no continuity. Connectors are not seated properly in the bulkheads from the backside. That happens more often than I wish it did. No patch cords. The connectors are bad and they fail ORL. Sometimes we'll test and we'll realize that the customer is going to need to put in some chromatic dispersion compensation. And sometimes it's going to fail PMD, Polarization Mode Dispersion. And the report that you get at the end will give you some suggested corrective actions. So I've mentioned dispersion a couple of times. Let's talk about it. Those of you that are not familiar with dispersion, It is the spreading out of a light pulse as it moves through the fiber. There's a couple or three different ways that applies in the single mode world. One of them is going to be chromatic dispersion, which is a combination of material dispersion and waveguide dispersion. The part that we're going to talk about most is the part that involves wavelengths. The different wavelengths are going to propagate through the fiber at different velocities. And while we talk about 1550, or we talk about discrete lambdas in a DWDM world, there's still a width, a spectral width to the pulse. There are no truly monochromatic light sources. So when I talk about 1550, I'm also talking about maybe as far down as 14, no, let's see, from 1550 I might go down to 1545 and up to 1555. And those different wavelengths are going to travel at different velocities. And as they do, they're going to start spreading out. That is, in essence, chromatic dispersion. Now, chromatic dispersion creates that limit that I mentioned at the beginning of this webinar. We're going to be limited for either the data rate on the existing fibers, or if we are locked into a data rate, we're going to be limited on the length of the fiber before we have to completely receive it and start over. Now, how this works, if you look at the two images here, the image on the lower left shows us our input signal. The top one is at 2.5 gigabits. The one at the bottom is at 10 gigabits. In fact, these are probably not to scale. Those 10 gigabit pulses or ones and zeros would actually be a little bit narrower. So we go through a length of fiber, and the red line indicates the dispersion or the amount of spreading of the pulse. Well, at 2.5 gig, we can very easily still see ones and zeros. But you'll notice at 10 gig, the same amount of pulse spreading or the same amount of dispersion gives us no zeros. Pretty soon we start getting bit errors, and the phone's ringing and the sky is falling, and basically we can't go 10 gig with the amount of dispersion that's indicated by this piece of hypothetical fiber. So you see, we are limited in our pulse width, or rather, excuse me, in our bandwidth, or we have to go a shorter distance with the higher bandwidth. And therein lies our tightrope that we walk. We start getting inter-symbol interference. Ones get muddied up and zeros disappear. And we start seeing ones instead of zeros. And there's the bit errors that we were talking about in the previous slide. So you can see how quickly the bit errors start up and the links fail. Now, dispersion was never really an issue. We talked about those original networks with low transmission rates. Regeneration stations were used. We didn't have EDFAs. We were using a single wavelength, and we kept it near the zero dispersion point. When we moved to 1550, we remanufactured the glass, redoped it so that our zero dispersion point went with us. And, you know, we didn't have any real problems. But now we're pushing further and further. We don't have regeneration stations. We're pushing on out. We're operating at multiple wavelengths, and dispersion is now an issue. So again, I mentioned that chromatic dispersion was the sum of two different types. Material dispersion is the part we've already talked about. Because of the quality of the glass, the wavelengths travel at different velocities. And then waveguide dispersion is simply part of the light signal is traveling in the cladding next to the core. And the light traveling in the cladding is moving at a different speed. So over distance, it's going to have a pulse spreading effect as well, because just a portion of the signal is moving faster. You'll notice that with any dispersion, we start talking about things moving at different velocities, we get the pulse spreading. Now, what are our limits? Well, that's a good question. And hopefully this slide will at least start you down the path towards your answers, because they're going to be subtly different for each person and each system. Okay, so the chromatic dispersion, we're going to specify picoseconds per the nanometers times the kilometers. Very often you'll hear it just referred to as, so many picoseconds. But it is most commonly picoseconds per the nanometers. The lambda zero, or the zero dispersion point, is that wavelength where there is no chromatic dispersion. The problem with the older fiber, the old SMF-28, which is the G.650.3 fiber, had about 17 picoseconds per nanometers times kilometers at 1550, and it caused us untold grief. So we had to move lambda zero to cut down on the dispersion. So here are the CD limits. Now, these are not hard limits, but it gives you a good basic idea of where to draw the line. So 2.5 gigabits, we can have up to 16,000 picoseconds of delay, and this still work. That means that with standard standard single mode fiber, we could run 940 kilometers. With the newer fibers, the NZDS, which is like the third or fourth generation of fiber, we can run 3,640 kilometers without any kind of CD compensation. But 2.5 gigabits isn't getting the job done anymore. 10 gigabits. 10 gigabits, we can have up to 1,000 picoseconds. Okay? That means we can go 60 kilometers on standard single mode fiber. With NZDS, we can go as much as 230 kilometers. Now 40 gig, here's where it gets a little bit scary. At 40 gigabits, we are only allowed to have 63 picoseconds of delay before we fail. It means we can go a rip-roaring 4 kilometers on standard single mode fiber. Even on NZDS, the newest, niftiest glass made, we can go 14 kilometers. So you see from that previous slide, if we want to go a long way, CD limits how fast we can go. But if we're locked into a speed, such as 40 gigabits, CD limits how long our fiber link can be. So in a world of going further, going faster, sometimes we have to choose. Or we have to compensate. Now with chromatic dispersion, there are compensation modules that are available to us that will allow us to compensate and pretty much fix the problems, and we can continue. The thing is, with the discovery of that and the CD compensation and pushing on to a longer distance, we then found polarization mode dispersion. Now, polarization mode dispersion is based on the idea that single mode fiber or single mode signals actually have two polarization axes the same way as radio. It's not surprising. It's an electromagnetic signal. It's just operating in the infrared portion of the spectrum, but it's not going to act in a lot of ways very different than radio, particularly in the idea that we have, what in radio we would call a vertical and a horizontal axes. With light, it flips a little bit, so we just call it X and Y. But we have two signals. And if we have any kind of asymmetries in the core, if we have any stresses during the distribution or during the installation, we can add stresses to the core cladding boundary that will cause one polarization mode to move at a faster rate, or more appropriately, one of them to be delayed. So that's polarization mode dispersion. The problem is that a real fiber is a randomly distributed collection of these local portions. So the stresses are not evenly spread. The stresses are not per kilometer. They're random. And depending on how we splice it, we could either compensate or exacerbate the issue depending on the simple rotation of the fiber when it's being spliced in the machine with no knowledge, because we can't look at the fiber and say, oh, this is going to give us dispersion in that direction and this one's going to be, you can't see that. So a guy out doing the fusion splicing is just picking up the fiber and splicing it just like he always has, just like he's supposed to do. But with these randomly distributed birefringent portions, we don't know. So we have to test this. It's not even engineerable. CD, at least we have some idea and we can do some engineering on the front end. We still got to test it to make absolutely sure. And we'll talk about that in just a moment. So here you can see the X and Y axes. If they have a section where one of them is delayed, you start getting a delta T or a time delay. And any kind of difference in time is dispersion. It spreads out the pulse. Ultimately, zeros get covered up by ones, and we get bit errors and link failures. Some of the reasons that we might have this would be lateral pressure, impurities in the doping, the fiber core being off center, the fiber core not being circular, perhaps an air bubble in the core. Up until 1997, we were allowed a certain amount of non-concentricity, meaning that the core could be off center by a certain amount, and we were allowed to have a certain ovality to the core. Now, with the advent of the newest fibers, NZDS, and then they changed the manufacturing process for all of them to tighten up on those tolerances on the core geometry, cutting down on PMD issues in the field. I said cutting down, not eliminating. Nothing eliminates PMD. So we might have a fiber defect, geometric. We might have some stress asymmetries. We might have some external stresses, lateral pressures from wind, In fact, I've tested fiber for PMD on a windy day, and your numbers change just from the wind. So, all of this can be pretty, intimidating. And but understanding what you're dealing with is the first step toward mitigating any of the issues and learning to work with the fiber that you have, or if you're hanging new fiber, to make sure that you get the proper product. Now, just like CD, we have some PMD limits. And I'm not going to get into distances, because really distances, whereas CD we talked about pretty linear. So many picoseconds times the kilometer, or per kilometers times the, or time per nanometer times the kilometers, you get the idea. It's pretty linear. CD is done as a like calculus, and it's expressed as a ratio of picoseconds divided by the square root of the kilometers, and it just gets weird from there. So I'm going to tell you how much average group delay, differential group delay you're allowed. Each fiber link is going to have to be evaluated for and tested for PMD to see how much you have. Again, we're going to look at the standard pulse widths, 2.5 gigabits. We can have up to 40 picoseconds. 10 gigabits, we can have 10 picoseconds. 40 gigabits, we can have 2.5 picoseconds. Again, how far that's going to get you is going to depend on the age of the cable and the fiber, when it was manufactured, how it was handled, whether it's underground or aerial, because aerial plant's going to have wind effects, which is going to change your PMD levels. So why is characterization important? Here's just a few examples. We're going to look at the type of incorrect information we received or we had in our possession before. We're going to look at its impact, what the solution was, and how much that cost us. Okay, so first one, the actual loss is higher than the original data used to design the network. So now where we put an amplifier will no longer work because it's too far out. We've got too much loss, and now our amplifier doesn't get enough signal coming in to work. So the solution, we have to buy 2 more amplifiers. We've got the original amplifiers. They cannot be utilized because they've probably got dispersion compensation for that particular length of input. So now we've got, $4,000 per amplifier. We're looking at $8,000 to $20,000 in cost because we didn't test it before we went out and finalized the design. If the actual loss is lower, if we had signal regenerators planned, they may not be required. We've already paid for them. We could have purchased $40,000 worth of regen gear that's not needed. And now it's sitting around being a doorstop and something to dust once a year. Okay, if we get the wrong fiber type, it's possible that we've got differences in loss, differences in chromatic dispersion. Now that means that all of our dispersion compensating modules are now wrong. We're going to either undercompensate or overcompensate. So now we're out buying new dispersion compensating modules, or DCMs, at $7,000 a pop. And the original ones are probably not even used because they were for the wrong amount of CD. Distance being longer, we're going to undercompensate for CD because we're going to have more fiber, more chromatic dispersion. Now we're still looking at that 7,000 per DCM. Or if it's shorter, we're going to overcompensate, which is going to push down too far and cause signal problems, so we're going to have to go out and change all of our DCMs. $7,000 a pop. All of these problems could be identified through full characterization testing. So let's look at the tests. We're going to break them down, and then I'll take some questions. Now, if you do have questions, the best place to put them is in the question box on your dashboard. Your GoToWebinar dashboard will have a question box. Put the questions in there, and I will answer them at the end of the presentation. See, I've already got a couple of questions in there that we have to talk about at the end of the presentation. So, first thing we're going to do after we've cleaned and inspected and cleaned some more and hooked up our connectors, is we're going to look at bidirectional loss. Our setup is going to involve cleaning the reference patch cords because we clean everything before we plug it in, right? We're going to reference out our test leads. It's going to take about 20 seconds per fiber that we're testing. And then these results will first establish continuity and will help determine the loss across the link itself. And the equipment we're going to use here is a power meter light source, basically an optical loss test set. Now, optical return loss. Optical return loss is a measure of all returned light, whether it's backscatter or reflections at connections. It's a measure of all returned light. So our setup on our ORLs, we're going to clean our reference cords, of course. We're going to reference out our patch cords, and we're going to mandrel wrap the opposite end if it's required in the reference process. The run time is about 10 seconds per fiber. Doing this, we will be able to look at the amount of reflection and which side the reflection's on, which is going to tell me which side's the connector dirty. Now, if we've done a visual inspection and cleaned or replaced connectors before we ever start this test, we should pass ORLs. That's pretty straightforward. A bigger number is better. It's a little counterintuitive to talk about loss and the bigger number is better, but with this formula, a bigger number is better, and with DWDM, you're going to be shooting for 30 or greater ORLs. We've got to keep our reflectances down so we don't overdrive and have ringing, and so we've got to keep reflectance to a minimum. The equipment used is an ORL meter. Now, bidirectional OTDR testing. Again, I say that you should shoot the wavelength you're operating and at least one higher, because we will be able to see macro bends. We'll be able to see installation problems and address them before they become outages down the road. So our setup, we're going to determine the range, set the resolution. We're going to look at our pulse width and averaging time. Set all of that, put all of that information in, make sure that everything's set up on our OTDR to run properly. Then the runtime is the averaging time times the number of fibers to be tested times the wavelengths. So if I'm shooting 2 fibers or 2 wavelengths, maybe 1550 and 1625, I'm going to shoot I'm going to set it up for a 30-second test. Then basically I'm going to be a little over twice 30, once for each wavelength on the testing time, then time to move it to the next fiber and hit the button to start the next test, where we'll have a little over twice the testing time. So again, with a 30-second test, I'm looking at about a minute and a second or two, because it does take just a second to switch from 1310 to 1550 or from 1550 to 1625. So, you're going to be looking at a little over a minute per test. Then you've got time to move it to the next patch cord or next connector and test it again. So that's how you look at the runtime on bidirectional OTDR testing. And then this has got to be done from the other side as well, as a separate test, so you'll have the same time lag there as well. The results we're going to get average loss per kilometer. We're going to get the location and loss of every event, every artifact, every splice, every connector, everything. We're going to use this, we're going to save this trace, and that is going to become the benchmark that we're going to use in all future testing, all troubleshooting. We're going to know exactly what the plant looks like, usually at its best. And then that saved trace becomes the benchmark that you aim for with any subsequent testing. So say the link fails, you realize that maybe there's a problem with the fiber. You shoot the fiber, you know what it's supposed to look like because you saved your benchmark. Then you can look at the new trace, look at differences, and perhaps identify the location of an issue much more quickly. And it will give us the length and the loss of the fiber. So those are all the results that we get from an OTDR bidirectional test. Now, CD, we're going to typically shoot a CD from A to B, looking at wavelengths from 1520 to 1620 with a 10 nanometer increment. So what that means is I'm going to look at 1520, 1530, 1540, etc., 1610, 1620. So we're going to have to set up, we're going to enter the correct test file. We're going to make sure that we've got the length from our OTDR test entered as the length for this test so that it can give us our correct data. And we'll have all of this set up. It takes from 2 to 8 minutes, depending on the test equipment, times the number of fibers that are being tested. The results is we're going to get a very detailed report on CD. We're going to find out what the chromatic dispersion was at each one of these wavelengths we tested, and we will know precisely how much compensation is going to be needed between the two test sites. That's vastly important, because if we undercompensate, we're never going to catch up and will ultimately fail. If we overcompensate, we're going to distort the image by crunching it too much, and we're going to ultimately get four-wave mixing and other issues that will then cause us to fail. So getting that measured chromatic dispersion to confirm our engineering is absolutely critical to making sure your plant works today, tomorrow, 10 years down the road. at the wavelength you're trying to operate and the bandwidth. Now, PMD testing, we're going to have some of the same setup. We're going to put in all the correct test files. We're going to set it up for distance. Then the runtime is typically 10 seconds times the number of fibers times 3, because it usually runs the test 3 times and averages any results. Because like I said, any movement is going to give it some subtle differences in PMD. Now the results is we're going to get a complete report on polarization mode dispersion. We'll be able to look at how that's going to affect the transmission rate that we're looking for, and be able to determine pass and fail about 10% of the, for standard 10% bit time. And typically the CD and the PMD analyzers plug into a modular OTDR platform. But sometimes they're so big that you end up swapping modules. So in the entire test, you've got time between tests with additional setup. So the time to test, how long is it going to take me to do this test? On a long haul fiber with a very long distance on it, I could take an hour and a half to 2 hours per span, which means that with travel, I may get 2 or 3 spans per day. With a metro in town, shorter spans, it could go very quickly from 45 minutes to an hour and a half. And that's going to allow me with driving to get 3 to 4 spans in an 8-hour workday. So those are some of the numbers that you're going to look at. So the data, what are we going to get? We're going to get a list of the tests that are taken, a summary of the results, exceptions and recommendations. We're going to get interpretation of the results. Someone will typically look at all of these results and tell you if this is good or this is bad, what's good, what's bad, and you'll get this full detailed report, including passes and fails on your CD and PMD at the bandwidths you want to operate. So those results, I've already kind of summarized this, but you'll get the summary of all the tests. Complete documentation package will include all of the files saved on the test equipment. You'll get a list of the limitations for transmission rates and what it's going to take to upgrade. You'll get recommendations for corrective actions and acceptance, that will get it to an acceptable point. And you'll get exceptions and recommendations expressing what can be done. Again, that kind of ties in with the corrective actions. So I see we've got a few questions in the question box over here. So I'm going to move the microphone and come over here and read the screen. So we have a question: when working with chromatic dispersion issues, is the total length of cable a factor when deciding if pre-compensation tactics or using dispersion compensating fiber at the end of the length would be more effective? Let me reread that to myself. If total length. Oh, when you're trying to decide between pre-compensation tactics or using dispersion compensation at the end of the length. The total length is, of course, going to determine the amount of dispersion you have. Most dispersion has to be corrected after it exists. So trying to look at pre-compensation really isn't going to have as big an impact as allowing it to disperse some and then correct it back to a good starting point before it gets out of hand. Because once it gets to a failing point, no amount of compensation is going to give you the zeros back. So the best course of action is to allow it to compensate to a certain level and then compensate. Or let it disperse, then compensate, disperse, then compensate. And you always want to get back to a baseline. And this is very typically done at the amplifiers. Depending on your loss and depending on your bandwidth, you may have to compensate in between. But yeah, I mean, generally I would expect to go and let it disperse and then compensate, because the pre-compensation is just going to give us some of the same issues that overcompensation would give us if we did that at the beginning. So I hope that has helped with your questions. If there's any follow-up question, please put it in the. Okay. Yes. Thanks. All right. Good. I'm glad we could help you out. So next question is, what would be a good value for the reference patch cords? Well, I mean, if we're talking about single mode fiber and we're looking at, a 20 meter patch cord, I would almost not be able to see the loss. If I'm looking at 1550 and I've got .22 per kilometer, and I've got a patch cord that's only, 100th of that, I should have what, .002 kind of loss in the fiber. I'm allowed to have .5 in each connector. So, if I've got more than a couple of dB in that patch cord, I'd be looking for a new patch cord. I'm hoping that answers that question for Mr. Latonia. I hope I pronounced that correctly. And then another question: what can be the cause what causes the ORL fails? ORL fails are bad connectors, dirty connectors, contamination, scratched connectors. Basically, if you're picking up on a theme there, it's all about connectors. At the very first test, or very first thing we do is the visual inspection of the connectors, and we clean, and then we inspect, and if it's not clean, we clean it again, and we keep doing this until we either get a clean connector or we give up and replace the connector. And then I've got a brand new connector to inspect and clean before I ever plug it in. If we do that and we have good clean connectors, then we're not going to fail for optical return loss. ORL fails are all about connectors. And one quick pointer: if it fails in one direction and not the other, say it passes A to B, but B to A fails, B side is your dirty connector, because it's going to have a much larger impact in close to the transmitter. So whichever side fails, that's your dirty connector. Go clean it. All right, next question. Why do we test at 1625 rather than 1310 or 1550? Well, usually I test at 1550 and 1625. 1310 is falling into disuse because all of our DWDM is taking place in that C and L band, which is 1550 and 1625 ranges. 1310 has a tremendous amount of loss comparatively, about half again as much loss per kilometer, so we're not going to be pretty much playing in that wavelength. If we're doing the high bandwidth, we're going to be running DWDM applications. we're going to operate in the C and L bands. So that's where we're going to test. Now I always say, and I said it twice today, the wavelength we're operating and at least one higher. Well, that's probably going to be 1550 and 1625. The reason for looking at a higher wavelength is to evaluate macro bends, because while splices and connectors have the same loss at any wavelength, relatively same, they're not wavelength dependent for loss. Macro bends will cause huge amounts of loss at the higher wavelengths. And the higher the wavelength, the more likely it is for a macro bend to cause losses. So by testing at 1550 and 1625, even if I'm not using L-band, it evaluates whether or not it's available for future upgrades, but it also lets me look at the installation of the fiber and whether or not there are problems with macro bends anywhere in the fiber. So I hope that answers that question for you. Check in the the question box here. Are there any other questions that anybody has? Now's the chance. Oh, somebody wrote a book. Wow, okay. Okay, so it says registration is important. Test to the fiber at each stage from construction or the laying of fiber to carry traceability network. I'm looking at someone here. I'm thinking maybe English is not the first language here, so let's work through this together because it's important that we get this. So what is the best measuring equipment for use in construction, installation, and maintenance? Okay. All right. Well, that's actually a very good question. Now that I got to the end of it, I'm going to tell you, this is one of those moments where I'm just going to be straight with you. Power meter and light source testing, ORL testing, and OTDR testing. Those are going to be your bread and butter. Day in, day out, we use those tools. In fact, I was just out on a job today where I was using a power meter to troubleshoot an issue in a building. We're always going to use power meter, light source, ORL testing, and that can very often be done. ORL tests can be done with your OTDR. So power meter, light source, and OTDR, those are your big tools, your big workaday tools. CD and PMD testing is very often done once. The equipment necessary typically costs $70, $75, sometimes $100,000 to use once. Once. That's it. If you want to upgrade, you might test again, but with a good analysis report, you should be able to see what you can do into the future. So before anybody completely faints on the other end, there are companies. Our sister company, some of the testing jobs I've been on was our sister company, AdTel Integration. We do testing for someone. So you can spend a few $1,000s paying a third-party tester, such as AdTel, to come out and do the testing, and you get the full report. It gives you some analysis for the future, some ideas of corrective actions you might need to take. It gives you correct engineering so that you can, if you recall that slide that had the incorrect data, the cost on the other side, you have correct data, you have correct length, You know how much your CD is. You know how much your PMD is. You can then work with your own fiber to move forward with your life and your project. And you don't have $100,000 worth of doorstop. Let somebody else buy it. And then, you know, they'll go out and do the testing. So that same email, actually sales@fiberoptic.com, will help you get to someone if you need some CD or PMD testing. We'll work something out and get you over to the AdTel guys. Let's see, I've got another question. Is IOLM measuring equipment used in other networks other than, I'm guessing, other than FTTH? Fiber to the home. Yes, IOLM is used in a lot of places. Again, being straight with you guys, I'm not a huge fan of IOLM. I think IOLM is a tool that too many times people depend on it instead of understanding how to read an OTDR. I would rather you guys attend my one-day class on how to look at an OTDR trace. But there's a lot of companies out there that are requiring IOLM. Anybody working with distributed antenna systems, we're getting a lot more of those. Tower guys in the U.S. are being more and more asked to turn in an IOLM trace that just says pass or fail. So IOLM is becoming much more prevalent in the workaday world. And yeah, and there's not a great deal of use of 1490 outside of our fiber to the home applications. But again, 1490 is down below C-band. So very often we don't look at anything lower than, 1520-ish. I will be honest, I couldn't jump right on the exact wavelength where we usually cut off at C-band. But 1490 is below C-band. And that is typically somewhere around the zero dispersion point for the new NZDS. So I want to thank everybody for being with us today. Thank you for your questions. If you have additional questions or anything pops into your mind down the line, you can email that to training@fiberoptic.com and put in the subject line webinar question or something like that that'll flag it and make sure it gets to the right people. So yeah, we're doing a weekly webinar series, and we welcome you guys to join us next week. I'm sure that if I asked nicely, somebody could tell me the topic. And look at the email that you received telling you about this one. We've got a whole series going on. And again, thank you very much for being with us. And we look forward to having you in our next webinar. Have a great day.